So my role here is twofold. I am the director of this institute that we have at Dartmouth, and the reason for that institute is that we now live in a very special time. It's a time where questions that were once part of what we call the humanities or religion are now also asked by scientists. And it turns out that there's been a big divide between the sciences and the humanities, to the point that they speak different languages, right? I go to a philosophy seminar, I don't know what the heck they're talking about. And the philosophers, with very few exceptions, like Patricia, go to a science seminar and they don't understand anything because we evolved into these very technical languages that only if you're very specialized, you can understand. But the problem is that we're now facing challenges, global challenges, where we just can't think only in one way about the answer. So we're talking about planetary future. How do we relate to our planet? What is going to be the future of our species given what's going on with our climate, for example? Those questions have a scientific part, but they also have a humanistic part. And the idea of this institute is to try to create a dialogue where scientists and humanists and everybody, including you, could actually participate, right? So we do this in 3 different ways. We have what's happening tonight, which is called the public dialogues. So I bring a very well-known scientist, a very well-known humanist, and I am the mediator of their conversation. Basically, they will talk. I'm just going to be watching them in awe because they're awesome. And then, I may say a few things here and there, and there'll be about 25 minutes where we'll be asking questions to one another before you ask us questions, right? But the big frame of this is that we want to ask big questions, right? Questions about who we are, questions of meaning, questions of what is the purpose of life. Why are you here? Are you here to just, go to your job every day and you're happy with that? Or are there deeper reasons for your existence? Do you want to participate somehow in the future of the planet, in the future of your community? Are there relationships between our future as humans and all the technology that we're creating and that is slowly changing who we are, right? Because honestly, if you go out one day and you forget your cell phone at home, that's going to be a bad day, right? Because you are not yourself anymore without that cell phone. That cell phone is part of who you are. It's actually a continuation of yourself, so much so that you all have apps, right? And those apps, of course, some of them are the same, but you're going to have your own apps. And a person's profile is very much a mirror of those apps that are being chosen because that is a reflection of you. It's an extension of you to the world. So in a sense, we are already blending with machines that tend to expand our social awareness and our cultural awareness. And of course, it always can be used for good and for bad, right? So tonight, I want to talk with Patricia and with Jill, 2 wonderful pioneers in their fields, about the future of intelligence. So what do I mean by that? Well, you saw here in the brief intro that everybody's talking about machine intelligence, right? Will machines, machines can beat, the best chess player, they can beat the best Jeopardy players, they can beat the Go player. Are these machines intelligent or not? And if they're not, will we be able one day to create a machine that is not just going to fulfill lines in a program, right? You write a code, the machine does that, but it will actually start writing code. And writing code in a way that is going to be creative in ways that we cannot anticipate. Is that going to be possible? And if that's possible, what will happen to us as a species? So there is this philosopher from Oxford called Nick Bostrom, right? So he wrote a book called Superintelligence. And in the beginning of the book, he says something like this. If we could develop a super intelligent machine, would we become obsolete? So he makes this parallel, like imagine us and the gorillas. The future of the gorillas is completely in our hands because you could go out there with machine guns and kill them all. But we don't do that, or not, because people are killing gorillas more than they should, of course, but we haven't done that because we have some moral standards that want to save that species. But we could, we have the power to do that. So the question is, what if those machines don't have moral standards? Are they just going to get rid of us because we are inconvenient? So the question is, are we engineering our own destruction through technology? So that's an ethical question, and that's a scientific question. You can't just think about it, oh, let's go crank, and hack the hell out of the codes and do this thing without thinking about the social, cultural, and moral implications of what's going on. So that's a perfect example of where you can have the two of them together. And of course, alien intelligence. Can life elsewhere in the universe be smart? Well, we don't know. But it's a possibility because it happened here, and as you're going to find out from Jill, we now live in this amazing time where we know that pretty much every star that we look out there has planets around it. Just pause for a second and contemplate that. In the Milky Way, our galaxy, right, there are about 200 billion stars. Just think that, all of them, or most of them, have 5 planets, right? So you're talking about trillions of worlds. And not including the moons, because, there are planets with lots of moons, like Jupiter has more than 60 moons. Imagine the night in Jupiter, it must be pretty awesome. But the point is that there is a lot of space. As Jill says, there's a lot of real estate for life to develop. So could there be life that is more advanced then? And how could we find out? And could they be listening to us? So, for example, Stephen Hawking has been making a lot of noise lately, scaring the heck out of us about all these different things, right? So first was the machine intelligence. So he and Elon Musk talk about the future of machine intelligence as possibly a threat to our species. And now the aliens too, right? So aliens also don't make small signs because they will see it and they'll come and they'll kill us because they're going to be the bad guys, right? And now, of course, the latest is that we only have about 100 years to survive as a species because we're just going to kill ourselves. So bad stuff, right? Heavy stuff. There are other ways of thinking about this which are much more optimistic, and I hope this will come up over tonight a little bit or during some of your questions as well. But the point is that those are fundamental questions that define who we are. Because as we think about machine intelligence and alien intelligence, what we're really doing is thinking about our own intelligence. What are we? We are weird molecular machines that developed in this particular planet and are capable of asking questions about meaning and about our future and about the why and the how of things. And that is a big mystery. So asking these questions about machines, aliens, we're actually asking about ourselves and figuring out how we're going to move on from here in this moment where all these things are happening to the future where we actually improve as a species and go beyond some of the dark parts of our history to create a society that is just and equitable. So without much further ado, I'm going to invite Patricia now to the stage. Let me introduce you to Patricia. Oh, the clicker. There is the clicker. So Patricia is Professor Emerita of Philosophy at the University of California in San Diego, and she's an adjunct professor at the Salk Institute there. Her research focuses on the interface between neuroscience and philosophy and has most recently written the book Touching a Nerve. She is author of the groundbreaking book Neurophilosophy and co-author with T.J. Sejnowski of The Computational Brain. Her book Brain Trust, What Neuroscience Tells Us About Morality, received the Prose Prize for Science. She has been president of the American Philosophical Association and the Society for Philosophy and Psychology. And she won the MacArthur Genius Prize in 1991. and the Rossi Prize for Neuroscience in 2008. She was chair of the UCSD Philosophy Department from 2000 to 2007. So let's all welcome Patricia again. Thank you.
Well, thank you so much. It's an enormous pleasure to be here in Chicago on a fine, sunny spring day. How absolutely magnificent. So yes, these are very deep and troubling issues in front of us. And so I want to start talking about intelligence where I feel I'm quite grounded, and that is with respect to the biological creatures that we are familiar with. Wolves, raccoons, ravens, and us. And I want to think about intelligence to the degree that we understand anything about it in terms of the physical brain. Now, I should just say at the outset that, of course, we don't have anything like a definition of intelligence in the way that we might have a definition of a protein. But we do, I think, have a general sense that it involves analytical possibilities, analytical capacities, linguistic capacities, and that's kind of the IQ test end of things. But of course, it involves so much more. It also involves what we might call practical intelligence, knowing what to do, when it's appropriate, and carrying on with it. There's also social intelligence, and there's moral or political intelligence, which may be in shorter supply that we would necessarily like. What we think at this stage is that cortex, that very special neural organ, that cortex is what makes mammals smarter than reptiles. Now, of course, bear in mind that it's very difficult to test that. How do you test a raccoon against a turtle, for example? But we think that mammals in general have a greater capacity for impulse control, for long-term planning, for assessing the value of a consequence, and so forth. And we think that cortex is the thing that makes the difference. Now, cortex is really a product of mammalian evolution. All mammals have it, from mice to rats to us, and no non-mammals have it. I'm going to say something about birds in a moment. Now, what you see in the slide is the kind of dark rind around the brain. This is a coronal cut, and that dark rind is the cortex. And the cortex is really different from every other structure in the brain. It has basically 6 plus or minus 2 layers, and it's highly structured everywhere in exactly the same way. If you look at a rat's cortex, a chunk of it, and then look at a chunk of mine under a microscope, not quite yet, you will see essentially exactly the same organization. And we don't see anything like that in the more ancient structures that we got, that we share with reptiles. Now, I will say a little bit about birds, and that is we know, of course, that birds such as ravens and crows and parrots and owls can be very intelligent in the sense that they can do extraordinary problem solving. They do not have cortex. Turns out, however, after many years of kind of struggling with how they could be so smart without having a cortex, that they do have a kind of analog of cortex if you look at the wiring pattern. It just doesn't have this magnificent 6-tiered thing that we do. The other thing that you should know about cortex, and this will come up again in the context of artificial intelligence, is that there are very specific cell types located on very specific layers and connected in highly specific ways. We know that if certain cell types end up on the wrong layers, as for example in certain mice, then they very quickly die of seizures. So cell types are very important, and moreover, different cell types respond to exactly the same input in quite different ways. And so we know, even though we don't know precisely what the function of them is, we know that they're very important. And finally, of course, there is the matter of connectivity, because it's all about how things are connected to each other. This slide shows a schematic of neurons with little spines, neurons in cortex, and it's on the spines where contacts are made, where synapses are made. And we know that one of the most astonishing things about cortex is that it is a big learner. And that all mammalian babies are born with very immature cortex, and that cortex gains structure as the animal learns about its world, learns to make models of the way the world works, both its physical world and its social world. So now let's think a little bit about machine intelligence. There's so much more to say about cortex, but I've only got 10 minutes. As you can see, I'm very fond of cortex. But, all right, so machine intelligence. So there are certain things that have been noticed for many years that animals can do almost effortlessly, but that write-a-program machines can't do, like recognize a cat. When the cat is partly in shadow, when the cat has lost its tail, when it only has one ear, when the lights are bright, when the lights are dim, it can't handle that kind of complexity. And so in the 1980s, many people looked at cortex and how it learns and changes its structure to embody that learning. And thought, well, look, if a rat can learn by experience to recognize different faces, and if that learning consists in just changing the synaptic connections between neurons, why can't we build a machine to do that? And that was really the birth of the idea of artificial neural nets, which didn't really come to fruition until there was sufficient power in the hardware to make it possible to make really big neural nets. Now, I show you here in this slide a very schematic neural net. The basic idea then is to have kind of pretend layers with pretend neurons. I don't mean that sarcastically. I mean that they're just very, very simple. And they have kind of pretend synapses on them, which can change. That's the basic architecture of artificial intelligence in deep learning and in machine learning as we now know and love it. There is an input, for example, faces, where they might be represented in terms of numbers. The input goes through the layers, and an output is put out at the end. But the machine has to learn. And that took a lot of mathematical ingenuity to figure out the algorithm whereby you change the synaptic weights of this artificial neural net. The basic idea is to say what we say in the game of search. Warmer, colder, 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 much colder. And when the algorithm feeds that information back through, so that's the bottom line, the error signals, it feeds that information back through the neural network, causing the pretend synapses to change their weight, to become stronger, to become weaker, or maybe in some cases to stay the same. Over millions of trials, a machine will then learn to recognize, for example, handwritten numerals, a huge problem for the write-a-program, for the coding style of artificial intelligence. Piece of cake, basically, for a learning machine. It will learn to recognize faces. Now, as Marcelo mentioned, one of the things that was very dramatic in the artificial intelligence world in 2015 was that a learning machine, AlphaGo, beat a world champion Go player. And Go, as I'm sure you know, is a very, very complex board game. He beat the world champion Lee Sedol 4 games out of 5. It was an extraordinary achievement. And because it was so extraordinary, I think it provoked people like Bostrom and others to think that if a machine can learn to play Go, it can do whatever it is that we do, or rats do, or raccoons, or ravens. Although I was very impressed too with that, and it is without doubt a stunning achievement, I now want to look a little more closely at that. Just look at the two top pictures of brains. This just indicates the number of parcellations, different areas that cortex seems to have. And when you have a deep learning machine, you will get much more in the way of learning capacity if you have many, many, like hundreds of layers. And we think that each hemisphere has, in the actual human brain, about 180 different layers or parcellations per hemisphere. Now, one of the things that we do, and rats and monkeys and all kinds of things do very well, is survive and thrive and make decisions. And much of that comes internally from the brain itself. It isn't part of its input. And in this diagram, I want to just remind you that cortex all by itself is just a hood ornament. It's nothing. It can't do anything interesting by way of helping the animals survive. It must have the appropriate sorts of connections to the deep underlying structures that regulate goals, emotions, motivations, and so forth. And none of that do we see in artificial learning machines at all. And I think the aficionados at Google and Facebook and so forth who are in the machine learning business realize that one of the things that animals and certainly humans can do is what we describe as actions with common sense. And that kind of means that you draw, and this I think is a problem for current machine intelligence. You draw on widespread background knowledge, integrated, and then relative to your goals and the current situation, you make a behavior. And so in this instance, this is a failure of common sense because there's some sort of failure to recognize the relevance of the current situation. So far, all of the artificial intelligence learning machines that we have seen do only pattern recognition. They can only classify. They cannot do decision-making relative to a kind of circumstance, relative to goals, needs, motivations, and so forth. Now, I don't say that they can never. It's just that from my discussions with people in the business, there are really two kinds of ideas. One is just do more of the same and by God we'll get there, which I kind of doubt. And the other is there are serious problems about how to have an intelligent machine do something like make common sense decisions where that requires integration across such a vast range of knowledge and recognition of what is and what isn't relevant. It also involves something that we really do not understand about natural brains, and that is how attention works. And I want to show you an example of failure of common sense with regard to attention. Just bear with me. Okay, and so the complexity of the non-cortical structures in their contribution to these ongoing events, having control over or contributing to what we pay attention to, what we deem is relevant, what we think is irrelevant, and so forth. We really do not have, in neurobiology, a handle on it. Now, it's conceivable that it's much easier than we think, but these sort of sobering, cold thoughts come to me when I am invited by Stephen Hawking and Bostrom and others to get very excited about the possibility that superintelligences are going to doom us. Francis Crick used to say that you can really only make a realistic prediction in science about 5 to 10 years out. That's the prediction horizon. After that is just guessing. And I kind of feel that way in this particular instance. Now, this is not that I'm indifferent to the human plight or anything of that nature. It's that I don't want to get very excited about something that is totally unrealistic. And there are realistic dangers that are very immediate. And one, of course, is a pandemic. Last year, there were something like 2 million people in the US who contracted infectious diseases that were resistant to all antibiotics. 23,000 of them died. And more antibiotics are now being shelved because the bacteria are resistant to them. I worry much more about that, actually, than I do about a super intelligent machine taking over. Thank you.
Thanks, Patricia. Okay, so we now move on quickly to our next speaker. So Jill Tarter, she holds the Bernard Oliver Chair for SETI Research, SETI's Search for Extraterrestrial Intelligence Research at the SETI Institute in Mountain View, California, and serves as a member of the board there. Tarter received her Bachelor of Engineering Physics at Cornell University and a Master's and PhD in Astronomy at the University of California. She has spent the majority of her professional career attempting to answer the old human question, are we alone, right? The question we all want to know the answer, by searching for evidence of technological civilizations beyond Earth. Since the termination of funding for NASA's SETI program in 1993, she has served in a leadership role to design and build the Allen Telescope Array, and to secure private funding to continue the exploratory science of SETI. So if you want to be participatory on this, fund SETI. Many people are now familiar with her work as portrayed by Jodie Foster in the movie Contact, but more to the point, there is a new book coming out, which is an authorized biography of Jill Tarter. It's by a science writer, Sarah Scholes, called Making Contact. And their book is coming out in July. And please, everybody, let's welcome Jill. Thank you.
So you've heard Patricia's wonderful exposition about human and machine intelligence. What about the extraterrestrial? I'm going to try and change your perspective, and I want to make you think about this fact, that you are made of stardust, quite literally. It takes a cosmos to make a human. The iron in the hemoglobin in your blood, the calcium in your bones and in your teeth, they were all cooked up in the interior of massive stars that blew up billions of years ago. So in fact, our story, the story of humans, began billions of years ago. Our universe was born in an immensely energetic, dense, hot explosion, something like 13.8 billion years ago. Our galaxy was born 10 billion years ago. And we humans actually trace our lineage not just back through the centuries of our families, not just back through the millennia of our civilization, its buildings, its arts, and its many experiments with governance, not just back the millions of years since we branched off from the great apes, not just back the 2.4 billion years during which our atmosphere has been perfused with oxygen thanks to the photosynthetic labors of cyanobacteria, not just back to the 4.6 billion years ago when our sun and planet were born, but back another 4 or 5 million years when giant molecular clouds were contaminated with the winds of Wolf-Rayet stars, and supernova explosion detritus. The ends of life of massive stars, supernova explosions, leaving remnants such as this modern remnant. The stuff that got incorporated into the stars, the planets, to life, to us, and which may happen again in the future to this modern remnant. We are made of stardust. And it's taken a millennia or so to piece together this scientific story of where we came from. And we continue down this road of inquiry because we're curious. We want to know more. We want to know why we're here and how we fit in and what else is out there. And of course, is anybody else there? And as we journey down this road, people, my colleagues, astronomers and astrobiologists, have a different perspective on what it really means when we say here and now. This is a much more broad cosmic perspective, and I think it's something that we should spend more time sharing with the public, with people who are our leaders for our near and long-term future. We need to share this perspective because it's important. It matters to our long-term future. So here, that's simple, right? We're here in the Feinberg Theater within the venue 610, right? In Chicago, Illinois. And we're all now pretty much around the world comfortable with this kind of Google Earth perspective. But from the altitude of low Earth orbit satellites, we'd see ourselves as here. And since 1968, when Bill Anders took this Earthrise picture as he was coming around the limb of the moon, we've been able to see ourselves from this perspective. This is our first truly cosmic perspective, seeing ourselves as a single entity floating in space. Okay? Actually, in 2013, the Cassini spacecraft, which has been orbiting Saturn, turned around and looked at all of us. They sent out a memo. I hope you went out on the lawn and waved, right, when Cassini took this selfie. There's a white dot there. And that's us, all of us. And it was done earlier in 1990 when the Voyager 1 spacecraft going past Neptune turned around, looked homeward, and saw this pale blue dot. That's all of us. And our sun is only one of 400 billion stars in a beautiful spiral galaxy like this one. Now, nobody got a spacecraft out there to turn back and look at this, right? This is another galaxy which is analogous to our own, and we're not even anywhere near the center. We're out in the boondocks. And that galaxy, our Milky Way, is one of 200 billion other galaxies in the observable universe. So those white dots, they're not stars. Each one of them is a galaxy with hundreds of billions of stars. And as we look at these beautiful images from the Hubble Space Telescope and notice that some of those galaxies are smaller and fainter, we're reminded that as we look farther out in space, we're looking farther back in time because of the finite speed of light. And so we have to encompass now as being the current epoch of evolution of a galaxy, of a universe that started about 13.8 billion years ago and has gone from the Big Bang to big brains and is going beyond. We have to encompass this sense of time and our place within it. So here are two really intriguing images. On your left, right, is an image of a neuron. Right? Patricia was just talking about this. It's only a few microns across. It's in a mouse brain. And on the right, that's a baby picture, simulated, because no one was there to take it, but a baby picture of our universe showing the birth of galaxies in the knotty tendrils of the cosmic web. And do the similarities in these structures tell us anything about what to expect beyond Earth when we go looking for intelligence? Well, here's the Milky Way from Earth. And one thing that has changed profoundly over my career is that we can now tell you with very great statistical certainty that there are more planets than stars out there. There is potentially a lot of habitable real estate, and now is the time to try and find out if any of it is actually inhabited. So my astrobiology colleagues are very eager to study the atmospheres, if any, of the nearby exoplanets, looking for biosignatures, looking for something that might affect the chemistry of the atmosphere in ways that only biology can. They're looking for microbes. I'm interested in finding mathematicians. And to do that, we have to use a search that looks for technosignatures. Because although we call it the search for extraterrestrial intelligence, we're actually using technology as our proxy for intelligence. That's all we know how to look for. And whether or not this kind of search will be successful is completely determined by the average longevity of a technological civilization. Because unless technologies persist for a long time, there will never be any two close enough in space and lined up in this deep temporal history of our galaxy to interact and discover one another. So Philip Morrison has a lovely way of stating that. He says that SETI is like the archaeology of our future. Right? If we ever detect a signal and there's information, it will be telling us about their past, because this tyranny of light speed means the signal has been traveling for a long time to get here. But if we detect a signal, we know that it's possible to survive our technological adolescence. We know that it is possible to become an old technology. Someone else made it through, and we can as well. So we've been doing this SETI job for about 50 years, and let me tell you, we've worked really hard, but if you take the 9-dimensional volume that we need to search for signals, and you set that volume equal to the volume of the Earth's oceans, to date, we've sampled one 12-ounce glass of the Earth's oceans. Maybe it's not surprising we haven't found anything yet, but what is very exciting is we're right now at a point where we can grab the exponential expansion of our computing capacity and our ability to build bigger glasses, to put them in the ocean faster, and to search much more rapidly. So in Northern California, thanks to the generosity of Paul Allen, we've built the Allen Telescope Array up near Mount Lassen. It currently has 42 dishes, and they're all hooked together by computing. So silicon is as precious for us as aluminum and steel. And the wonderful potential for this array is not only to build more dishes, maybe as many as 350 for more sensitivity, but to grab on to the Moore's Law exponential growth to be able to detect much more complex and many more signals at one time. In the optical part of the spectrum, we began doing SETI about the beginning of the 21st century. And here's a dedicated telescope built at Harvard University, which searches the sky looking for very bright, very short optical pulses, the kind of thing that a laser can do, but Mother Nature can't. And over the years, they've scanned the sky that can be seen from Massachusetts a number of times. More recently, Yuri Milner has generously promised a pledge of $100 million over the next 10 years for additional SETI searches in a project called Breakthrough Listen, where they will rent time on large astronomical telescopes and build back-end signal processors. Right now, they're at Greenbank, West Virginia, Parkes, Australia, the automated Planet Finder telescope at Lick Observatory, and soon, China's FAST telescope and the Meerkat telescope in South Africa. Now, we're looking for artifacts. We're looking for things that look engineered. And in 1973, Arthur Clarke told us about the third law, Clarke's third law. He said, any sufficiently advanced technology will be indistinguishable from magic. And so we've been imagining what that magic might be. We've been projecting forward our technology and looking for these kinds of artifacts. But more recently, philosopher Carl Schroeder has said, a really old technological civilization might in fact be indistinguishable from nature, because that's the only way that you can get to be old. As we look at exoplanets for biosignatures, we might look for strangely engineered, overnatural planets. And it's really hard to figure out what I mean by that, or anybody means by that. But maybe they artificially change their climates so there's uniformity in latitude. You don't have cold poles and warm equators. They might get rid of extreme weather over time. And ultimately, they might modify their star in ways that gives them the energy they need to do these things, to keep their world in homeostasis and natural. And of course, then what would an engineered natural world look like if the world were run by machines? And this is one of Nick Bostrom's nightmares, that we take insufficient care in building a super intelligent machine. We don't constrain and box it with enough security. We don't take enough time to think about what is a good goal, a moral goal, the right goal to give the machine. We might tell it to build 1 million paperclips, in which case the machine turns everything available into paperclips and paperclip manufacturing. We don't know what such a world would look like as we go looking, and we wonder, is this our future as well? So right now, when you don't know how to define what you're looking for, machine learning and artificial intelligence are beginning to give us, with these neural nets, some new tools. So we're going to try and do this in SETI, use machine learning to find patterns in noise that we currently are not searching for, aren't aware that are there. We've been working with IBM for the past 18 months or so, and we're going to be holding a hackathon in San Francisco on June 10th and 11th, and follow that with a summer-long code challenge. So if any of you are interested in this kind of thing, please think about contacting us, going to that website and registering it. And I'm just going to end with one last sentence from Caleb Scharf, the chairman of the astrobiology department at Columbia University. Caleb reminds us that on a finite world, a cosmic perspective is not a luxury, it's a necessity. That's the point of view that we all need to adopt in order to be able to manage and find solutions to those challenges that look so difficult now, particularly the challenges that don't respect national borders. Thank you.
Okay, well, I hope that inspired you. It certainly inspired me. Before we start, one quick announcement. In your programs, there is a survey that is something that my sponsors, these things don't happen for free. They cost a lot of money to do this. And in order for us to continue to do it, we need to have some feedback from you. So if you have programs, there should be some surveys in there. If you don't mind, please filling them out. we need that for statistics to tell my sponsors that we're doing an awesome job and they will come back and do this again. So thank you. Okay, so now we have time for conversation a little bit. So I'll just ask a couple of questions and then please feel free to ask questions to one another as well, okay? So let's start with Patricia. So the other day I was landing in San Francisco and taking, a cab from a lift, sorry, from the airport to town, and there were all these outdoors about artificial intelligence and machine intelligence everywhere. Like they're already selling it as a product. And I wonder if that bothers you, because I was sort of shocked by it, because I think it's a misnomer.
Well, I don't think it really matters if we call it artificial intelligence. I mean, doing really complex pattern recognition is a kind of intelligence. It's a tremendously important kind of intelligence. And I think the machine learning, deep learning, is going to have tremendous numbers of uses, without a shadow of a doubt. It's already being used in your smartphone, of course, and that's what Siri uses, so to speak. But it's being used in medicine to read mammograms and other forms of radiographs. It's being used all over the place, and it's tremendously useful. It's just that it's a very, very restricted kind of intelligence, and it's not the kind of intelligence that's going to lead us to the Bostrom catastrophe. Because to get from here to there, you need a huge amount of other stuff. For one thing, you need to have things that can learn 1 or 2 trials. It takes millions and millions of passes through a neural net. If you change one tiny rule in a very minor way in the game of Go, it turns out that AlphaGo has to start from scratch. I can teach a dog to make one tiny change in how it herds sheep. It will learn in 2 trials. It also is the case that every one of these machines can do one thing, right? It can recognize faces or it can recognize numerals, but it can't do the things that a sheepdog can do. It can't both herd sheep, bring in the paper, recognize faces, and learn not to dig holes. Well, it doesn't dig holes. So it can do one thing. Now, I don't want to diminish that achievement. I mean, it is a very, very important technological development. But people kind of talk themselves into frothing at the mouth about this. And it's not intelligence of the kind you see in a rat.
Okay. I want to go back to that, but before that. So Jill, I think, could you tell people a little bit about the Fermi paradox? Because that's something that is all over the place. People hear about it, and there's a lot of expectations and potential explanations. And I wonder if you can say something about it, and what's your favorite?
Well, paradoxes in astronomy have a long history. They can be extremely powerful. Observing Obler's paradox, observing that the sky is dark at night, finally leads us to understand that the universe is expanding. Very powerful structure. So people take the Fermi paradox seriously. It has its origins in Enrico Fermi coming to lunch one day at the Manhattan Project and saying, "So where is everybody?" And his colleagues understood that what he was doing is constructing a story which says that it takes, on a cosmic timescale, such a short time to go from the origin of technology to the origin of spaceflight and the ability to move among the stars. That if there had ever been anywhere, when, another technological civilization, that on times that are short compared to cosmic times, this previous civilization would have occupied the entire galaxy. They would be here, and they can make up all kinds of different models, doesn't matter, to within astronomical accuracy in a very short time. They're here. But, he said, they're not here. So it must mean that there can never have been another civilization with technology, that we are the first. And you got to take Fermi seriously, right? And this is an interesting proposition. And I say that it breaks down as a logical, philosophical, paradoxical structure because we can't say they're not here. Now, I don't mean that they're abducting Aunt Alice off the streets of Chicago for salacious medical kinds of experiments. I don't mean Bigfoot. I don't mean flying saucers. But go back to the how big here is and how deep now is. And we've explored even our local solar system so poorly that we would have missed any number of Coke cans filled with artificial intelligence that was, in fact, them. We can't even guarantee that we found all the big rocks with our name on it, and we've got a real vested interest in that one. So I think that we overestimate when we say that we've looked and they're not here.
Okay, great. Nice. Do you have any questions to one another?
Well, I'm sort of curious about when you think about what the intelligences might be. I mean, they might be really just radically different from us. I mean, they might be kind of big, smart gas bags or something. I mean,
really good science fiction novel called The Black Cloud about that.
Oh, okay.
Fred Hart.
Yeah.
I mean, what do you think they might be like, assuming that you're right, that it's very probable that somewhere out there are intelligences of some kind?
I can't answer that question. I look at where we came from, the building blocks that made us, that made your rats and your sheepdogs and the microbes, and might that process be repeated? Is intelligence actually something that will be selected for evolutionarily? And it's pretty expensive.
Yeah.
On the other hand, if there's any predator-prey relationship on some other planet, intelligence tends to ratchet that up pretty quickly. And I think that it's not unreasonable to think that there's something out there that can build and operate a transmitter, which of course is my cop-out on trying to define intelligence. Right? It can be a big gas bag if somehow it can manipulate the physical world in order to produce evidence of its existence over interstellar.
But it might be just like a bunch of dolphins who just don't have these things. You know, they've got fins and they can blow these wonderful bubbles and they can cooperate with each other, but they don't have this.
That's right, and they may not, I mean, they may be able to write poetry and sing poetic songs to one another.
Yeah.
The other thing they don't have is the ability to make fire. And that may indeed be necessary for technology. It may have to be a land-based, not water-based.
Yeah.
Right, because you need to be able to manipulate tools in order to develop technology. Right.
And get metal out of
And that would be a wonderful
dirt.
world to find, right? A world of dolphin philosophers. No kidding. But I don't know how to find it. I don't know.
I'd like that too.
Right. So back to, if you look at the history of life on Earth, right? It's kind of an amazing history if you think about it. And one thing that I think is important for people to keep in mind is that the history of life in a planet, in a sector, mirrors the planet's life history. So in the sense that what happened here will not happen elsewhere, ever. So because the history of this planet is going to be different, even if there are other Earth-like planets out there, they're not going to have exactly the same things that have happened here with all the impacts and the global sort of cataclysms that have happened here. So one thing that we can say for sure is that we are the only humans in the universe.
I think that's absolutely correct. And the other thing to remember is that the planet has shaped the life that's on it. But the life on this planet has also profoundly shaped the planet.
Exactly.
And so I think there will be this kind of, if there is life elsewhere, this sort of co-evolutionary development, but we have no idea how many different pathways there might be to creating something, again, that can build and operate my telescope.
Right, yeah, right. And going back to that, the artificial intelligence issue, can you tell us a little bit about, and this is kind of a harder question maybe, but I'm sure if there is one person that can answer, it's you, a relationship between the nature of intelligence and free will.
Oh, hey, yeah.
I mean,
No
she's
problem.
here, why not? Right? Might as well.
Well, I mean, there is one way you can think about it, and you know, in a small package, and that is this: that what you do see as a result of cortex is that there is a kind of looseness with respect to the more ancient structures and the reflexes that are controlled by genetics. So there is, if you like, a kind of slop between the decisions that are made by cortex in conjunction with the more ancient structures, and what you see in reptiles and insects, which is behavior that is largely, but not entirely, of course, largely under genetic control. And because cortex is so such a big learner, it means that people can acquire certain sorts of skills and habits. They can learn to operate in certain social contexts. Their reward system, which is ancient, interacts with the cortex in such a way that they acquire greater and greater impulse control and the capacity to see longer and longer into the future and to evaluate consequences of an option. And I think that's as good as free will gets. And so what we have in humans is not sort of different in kind, what you might have in a chimpanzee or a monkey. It's just a little bit more in the way of the capacity for impulse control or to deliberate before a decision. But we see those things to lesser degree in dogs and even in rats. I mean, there are wonderful experiments showing that rats can defer gratification very nicely, or at least most of them can. There are some that are really poor at it.
Same's true for humans.
And the same is true of humans, absolutely. And so I think that this looseness of the connection between genetically dominated reflexes and the cortex, which can interact with those ancient structures and modify the nature of those reflexes. That's what's really kind of amazing about the development of cortex. And it all came about, of course, because animals became warm-blooded. And once they became warm-blooded, they needed to be smart, because they had to eat 10 times as much as their cold-blooded friends. And as soon as you have an ecological constraint like that you got to eat 10 times as much, then Mother Nature, so to speak, saw to it that there were changes made so that certain animals had this amazing structure interlaced with the ancient structures that could do these things. And I think so in a certain sense, intelligence and free will are connected, but don't get the idea that a really, really smart mathematician has more free will than I do, right? I mean, he may be really socially very stupid or practically very stupid, even though he's a great mathematician.
Right. Okay.
So where does fire and cooking food come into that?
Well, I mean, it's very interesting about fire because, so us guys, Homo sapiens, we believe, have been on the planet for about 250,000 years. But there were, of course, hominins before that. We overlapped with Neanderthal for about 30,000 years, and there was indeed hanky-panky. I've got 4.9% Neanderthal genes.
You're higher than average.
That's way
Seriously?
above the...
No, it's quite a lot. It's quite a lot. But before that, there was Homo erectus, who appeared on the planet about 1.8 million years ago. So Homo erectus was very cool. They were small. They had a brain of about 800 cc's. So yours is about 1,500. So it was almost half your size. But Homo erectus had fire. And they knew how to use it. They presumably cooked their food. They had all kinds of stone tools. They made rafts by lashing logs together with vines, and they got themselves out of Africa to Indonesia. So before that, there were the Australopithecines, who were rather different, and they were not quite as bipedal, and they had other physical differences. We don't think they had fire, but every year, the archaeological evidence comes in, and we find that more and further back, we see the development of really quite extraordinary things by way of tools and use of fire and communication and so on. Yeah, and we're not the only ones, presumably, that had language. Almost certainly the Neanderthals had language. They may not have had as many vowels as we do, but you know, you get along with fewer vowels than we've got.
So Jill, you said something before that if there are intelligent aliens, they'll have to be kind and somewhat wise. Can you revisit that argument? Because I think that's a very important one for everybody to learn here.
That's the why is a nice girl like you taking a contrary point to Stephen Hawking.
Yes.
Yeah, all right, so.
I'm with you. So I think Stephen Hawking needs Prozac or something. It's a little depressed.
All right, so we're a young technology in a really old galaxy. And we frankly don't know whether it's going to be possible to grow old. But if you take the point that there are advanced technologies out there, advanced enough to be able to come and be a threat to us, the Hawking question, then they're going to be older. They're more advanced. It took them time to get there. And I think the fact that they are old enough to have that technology perhaps argues for the fact that they've had to get over, get rid of some of the aggressions that helped get them smart in the first place. And that cultural evolution might, in fact, lead you to become less aggressive when you figure out that you've got one planet and you've got to manage it with a certain number of individuals and manage it sustainably for a long future. I think perhaps there's something in that scenario that says you can't get old, you can't get that job done unless you're kinder and gentler. And so it's a contrary point of view.
Yeah.
I mean, Stephen may be right. They all may be sons of bitches and they're going to land here and we're not going to like it. But guess what? If they can land here, it doesn't matter. They're going to write the rule book.
Right. So here we are. So we're the only humans, and we have this very special, small, pale blue dot. And it's really this century, I think, that is a defining century in many ways. So all this new science is, I hope, forcing us to grow up, because that's the only hope we have. And then you guys, I don't see very well, but it looks like you're all younger than the three of us here, mostly anyways. This is...
They laugh at our jokes, so they must be there.
That's true. That's something that everybody should take to the heart and really try to make a change. And it happens with each one of us. You don't have to wait for the government to make things happen. You can make things happen yourselves too. So with that, we're at minus 16 seconds. So I'll end this conversation and then open to you guys to ask questions. Apparently there are microphones that are going to circulate, and you can ask questions that way. Thank you
now
very
we
much.
can see you.
Yeah,
That's
now
nice.
that's so much better.
Yeah, there it goes.
Hi. Hi. Thank you so much for sharing your knowledge with us today. I have a question about Mars and going to Mars. It seems that it would be possible within maybe 10, 15 years. How do you think that's going to impact your the part of science that you're working on?
Well, let me start by answering, but I think before we go there, we ought to figure out whether there are any Martians there. Because they might not like having us show up and ruin their planet for them. So this is a serious question. It sounded like a jokey answer, but it's a serious question about searching for life beyond Earth. Mars may, in fact, have evidence of fossil life or even extant life today beneath the surface. There's water somewhere on Mars. There's liquid water. And where there is water, there may be life. So we're very eager to explore Mars to find out if there's a second genesis, right? Is there life on Mars? And if there is it related to us? Because early in the history of the planetary system, Mars and Earth and Venus were all swapping rocks. And a microbe could actually have hitched a ride from Mars to Earth, seeded this planet, and so it might be that we're all Martians. Could be. Or, perhaps more interesting even, showing my bias, is that we could find life on Mars and it could be unrelated to us. All life as we know on this planet is closely related. We might find an independent second genesis of life on Mars, and that would tell us that life is ubiquitous. It's going to be everywhere out there if it happened twice in this one solar system. So, first of all, I'd like to check if there are any natives before we start thinking about exploring and perhaps changing the environment of the planet to be one that is more suitable to life as we know it. But I'm excited about the possibility for exploring and finding out what's there.
Thank you.
So, you know, it was mentioned that computer learning and technology only really does one thing, say playing Go or playing chess, or say a language program. Language programs are pretty good. They can even do speech now. Oh, yeah. And if you look at computers and that sort of information technology, we're only maybe 50 or 100 years into it at most. So the fact that we already have language programs, to me, means in another 100 years or another 10 years, they might get much, much better at a much accelerated rate of performing functions. So, I mean, why do you think that that won't happen, or they won't be able to do more than one thing?
Well, I don't want to say that I think it can't happen. And maybe in 100 years, something like that will happen. My point is really a more practical one, which is that certain of the limitations that we recognize quite well right now in learning machines, we don't exactly see how to overcome. And it may be that once we know more about natural biological brains, we will see how to overcome those. But if we take Francis Crick's rather practical also sort of take on these things, he used to say things like, well, you know, you really don't want to get too excited about what might happen 50 years from now, unless you're pretty sure that you can see a well-trodden line to that. And we can't in the case of machine learning. We don't know how to overcome some of the important issues having to do with goals and motivation. I know it's very easy to sort of wave your hands and say, oh, well, you know, we'll just make them smarter. But there are really significant technical limitations on that. We don't, for example, know whether you need very different cell types in order to do something like what brains do, in the way that, as I showed you, cortex has these very different cell types ordered in these highly canonical ways. Every unit in a machine learning device is the same as every other unit, and it don't matter at all whether it's way at the top or in the middle or down at the beginning. But boy, oh boy, in biological brains, it makes all the difference. So there are many technical issues, and it's, I think, just a little bit facile, if I may be rude, for Nick Bostrom to say, oh, there's going to be these super intelligences, and we better all watch out, and oh yeah, all right, you know, get on with it.
Actually, Patricia, one of the things that seems to me that it's got to be pretty soon, it's going to be a stumbling block, is the fact that we actually don't understand how these neural network black boxes really work. And we don't really understand what biases they've built into them themselves or that we put in initially.
It is true that there is much about the mathematics of big networks that we don't understand. Dinky networks, if they're 2 or 3 layers, we pretty much have that nailed, but you're absolutely right. So if you are looking at a learning machine that has hundreds of layers, millions of pretend neurons and billions of pretend synapses, we actually do not understand the mathematics. And that is one thing that mathematicians are quite excited about, because it's a job that they think they can solve. And they may well, but it is true that we don't currently have a sound grip on the mathematics of all that. But in a deeper sense, with regard to biological brains, there are fundamental things that we don't understand about why brains are the way they are and how they work, and how it's possible for a raven to learn in one trial how to solve a particular difficult problem. No machine learning devices, I mean, they require millions and millions of trials to do that. That may change once we get real neural net chips. You may scale it down to only hundreds of thousands. But that's still very different from what biological organisms can do. So there's something different.
Yeah, it's not just an engineering problem, perhaps, right?
Well, we don't know.
Well,
I don't think we know what kind of problem it is. It's partly a neurobiological problem. It's partly, I think, that we lack certain conceptual tools at the moment, actually.
I mean, the $1 million question, I guess, is, would these machines, which could be intelligent, be conscious?
Oh, I don't know.
Exactly. You know, because that is a complicated question, right? I mean, they will be smart. They will do many things. They're much smarter than we are in many ways.
No, well, they're not, though.
Well, they're fast at calculating. We cannot beat them, right?
I have no problem turning off my computer.
But I would like to know how many here would not have this problem.
Yeah, I don't know. I am very interested in the problem of the nature of consciousness. And unlike my friend David Chalmers, I do think it is a function of the biology. Right. He thinks it's a fundamental property of the universe, along with mass and charge. I think it emerges from the biology. But there are many things about the brain that we do not understand. We were talking about this before we came on. You know, we understand a certain amount of how brains change when they learn something. If I ask you now, do you remember your first kiss? I bet most of you do. We have no idea how that memory was retrieved. Absolutely none. Now, I could say, oh, I think it's probably a fundamental property of the universe, along with mass and charge. It just kind of gets right in there, and, you know, but I'm not likely to do that. And that's because, and similarly with consciousness, if you can affect consciousness with LSD and propofol and a blow on the head, and if it vanishes when you go to sleep and it emerges again when you wake up, it smells biological to me.
It's totally biological, yeah. But that doesn't mean it's easy to understand.
No, it doesn't mean it's easy to understand, but it doesn't mean it's like mass and charge.
Right. Maybe we need a perspective from a different kind of intelligence. That'll do it, right? Because then we'll have two things to compare to.
Well, yeah, when you only have an example of one, it's just damned difficult to figure out what's necessary and what's contingent. Yeah. It's only when you get multiple examples you can figure out, oh, well, you could have done it this way, you could have done it this way. Right.
I think we have time for one more question.
Okay, good. So, Patricia, my question kind of speaks to what you were just talking about with how much we don't understand about the brain already. So we know that there's a very small percentage of our brains that we actually use. And, you know, there's a sufficient amount of evidence with, like, monks changing their body temperature just with thinking and things like that. How much does all the stuff that we don't know about the brain, that huge amount of, you know, potential that we haven't tapped into, play into how you guys think about this? Because I hear a lot of perspectives around the way that we currently understand ourselves and our world, into kind of what you'd expect for what other consciousnesses, what other beings would need to use in order to have tools or fire or whatever we think that we need to have in order to survive. But, you know, how much does what we don't know impact how you think about that versus, like, not having certain assumptions going into it?
Yeah, it's interesting. I mean, let me say one thing first, and that is, I think that at any one time you're not using every neuron in your brain. That's true. But probably over time, every neuron in your brain has a job. So it's not like you could just get rid of some and nothing would happen. So that's thing one. And that's more true even of the subcortical structures, all of which seem to be really important. I mean, you can lose through stroke, for example, a chunk of cortex, and you'll still be very functional. If you lose even a tiny amount in your thalamus, you're hosed. So or your brain stem, you know, you lose consciousness, you're done. So, so that's one thing. But the way I think about what we don't know in the brain sort of goes like this, that over the last 3 or so decades, we've actually learned a lot about individual neurons and how they work. And it's, I mean, they're not simple as they are in learning machines. They're amazingly complicated. They're kind of computational devices in their own right. And we've also learned quite a lot at the sort of systems level, using things like imaging and scans and so forth, as well as various data from psychology. What's in between are neural networks. There's macro networks and micro networks and all of that connectivity. And that's where the big, big puzzles are. We don't know how individual neurons work with others to process information or to retrieve a memory or to collaborate on making a decision about this long-term plan rather than that long-term plan, to, you know, say this rather than that. We have no idea how neural networks work. And one hope is, and I think this is actually a fruitful possibility, is that there will be a kind of collaboration between the machine learning people, the artificial neural network people, and the biological neural network people to try to get some sort of real conceptual innovation about what's being done by neural networks, so that we can have a better understanding of how the brain actually does do things, like learn and remember.
So perhaps the future of intelligence is not so much out there, but it's in here through a connection of us and future technologies that will just be enhancers of who we are.
Enhancement is definitely on the cards, and I think it's really spectacular to see some of the progress that has been made in giving paraplegics and others capacity to use their brains to move a cursor, and hence to communicate in some instances for the first time in 10 years. And I think that's the thin edge of the wedge, and I have tremendous hope for that, because there are many, many people who have disabilities where this would be an absolute boon.
So IA as opposed to AI.
IA, industrial arts? No. Sorry.
Now I'm blanking on.
Intelligent aid.
Yeah.
Intelligent aid, yeah. Or intelligent prosthetics.
Intelligent
I suppose.
augmentation.
Yeah.
Augmentation, right.
Yeah.
Okay, on that note, let me just say in closing that if you want to know more about what we're doing, go to icethegoodice.dartmouth.edu. Have to make a distinction here. And all our conversations are video recorded, and we also have a blog, which you can continue this conversation elsewhere. So I would like to invite somebody, maybe no comments from the Chicago. Okay, let me finally thank the Chicago Ideas people. They've been awesome. This is incredibly professional, and we love being part of this. All right, so see you next time. Thanks for coming. Bye.